Syzygy episode 35, That Black Hole Image. Well, we're back for another episode of Syzygy, and this one's been a little while coming. I kind of feel like we're a bit behind on this one, but just in case there's anyone out there in the world who isn't aware, when was it? Last week? Last week there was a big announcement which was all over the papers, all over the news, made front page image on a lot of newspapers, which was the first image of a black hole. But it turns out is not the black hole we thought it was going to be. Emily, you're sitting opposite me here at the table in my living room. We did a podcast about this a while ago with the news that this image was coming. This was what, episode 20 of Syzygy? And we thought it was going to be something completely different. Turns out, no, we were wrong. What's going on?
Yes, hello. When we did episode 20, we were so excited about this telescope. We talked about the Event Horizon Telescope.
The Event Horizon Telescope, which, to be clear, is not a telescope, but we can come back to that in a minute. It's a bunch of telescopes, which is really cool. But we were talking about something completely different at the time.
Well, I think possibly because we've been so excited by other news about the supermassive black hole at the centre of our galaxy.
Yep, at the centre of the Milky Way, big honking black hole. And we were very excited about that. Why were we excited about that?
Because we found a star that was going to orbit super, super close to it.
That's right. That's right. Because, of course, that's been the way that we've been able to determine that these things actually exist in the past, is because we haven't seen the thing itself, the black hole itself. We've seen its effects, in particular its gravitational effect on a whole bunch of stars orbiting around it really, really fast at the centre of the galaxy. The only thing that could be causing that kind of motion of stars is a stupidly big black hole. And so given that observation and that news about the one in the middle of the Milky Way, and then this this collaboration of joined together telescopes around the world, the Event Horizon Telescope, we just assumed, well, any image that they take is going to be of the one at the centre of our Milky Way. Turns out not.
Yeah, I mean, we just naively assumed, that they'll be looking at that big one.
Yeah.
But it turns out there's even better candidates for taking an image of a black hole in other galaxies. And this is exactly what this image is of.
So we need to unpack this one a bit because there's just so much in here. But did you actually watch the news, the press conference?
I watched parts of the highlights. Yeah, it was really, really exciting.
I got to admit, I tuned in live. I was that excited. And it is always lovely to see a bunch of scientists and the way that they present their news. So just to back up a little bit, this is a collaboration which is worldwide, right? There are telescopes in how many places around the world?
Well, there's 8 telescopes and they span across North America, South America, Europe, so heaps of places.
And the point is, and we're not going to go into great detail on this telescope because we've already done that back in episode 20. If you're really interested in getting into the nitty-gritty fine detail, go and listen to episode 20 of the Syzygy podcast. But very, very quickly, these are all individual telescopes in their own right, radio telescopes, but the data is being very, very carefully correlated. And so they were quite literally trucking, CDs, tapes, massive quantities of hard drives around the world, getting the data in the same physical locations and multiple locations so they could cross-check to be able to get all of that data together, to combine these 8 telescopes into effectively one big telescope the size of the planet, which is awesome in any language. And so seeing these different teams getting up, because I think there was a press conference held simultaneously in Europe and in North America, maybe somewhere else, in Japan, I think, and seeing these academics or these researchers getting up and giving their press conference always just makes me smile a little bit because there's always something just a bit awkward about it, Do you remember when the Higgs boson was found at CERN and the entire social media just flipped over the fact that one of the leading researchers got up and gave her presentation in PowerPoint using Comic Sans font. And you just, what? You can't do that. Apparently you can. And this time around, it was a bunch of people in suits getting up and being a little bit awkward and going, yeah, but check this out. this is awesome. So it's worth going back and seeing some of the highlights of that. But I tuned in live, and it was very exciting because there was this big countdown, and it was synchronized in different places around the world. Big announcement. Everyone knows what's coming. We're going to see an image. But I think everyone was sort of, and we're going to see an image of the black hole at the center of our galaxy. And they went, no, we're looking at this one. And it was an image at the center of M87. 87. I was about to say 37. M87, which is a completely different galaxy. And it's a very long way away. But it turns out that the power of this Event Horizon Telescope is still enough for us to actually be able to see this thing, which is staggering. So let's talk a little bit about why that might be the case then. Why did they turn around and surprise us with an image of a black hole in another galaxy rather than our own? Surely the Milky Way black hole's closer. We should be able to see that better.
It is closer, but it's so the supermassive black hole at the center of our galaxy. We talked about how big it is, and it's big in terms of mass, right? It's huge. It's millions of times the mass of our sun. I think something like 4 million times. And that's a lot of suns you've got to poke into a very, very tiny region of space. Yeah. But by no means is it the biggest type that we have of these supermassive black holes.
So there's supermassive and then there's supermassive. I mean, to the naive observer... I think we
ran out of supers at this point.
Yeah, the naive observer would think millions of solar masses, millions of suns worth of stuff clumped down into a black hole. That's big, but you're saying, nah, watch this.
So M87 is a relatively close by galaxy. It's still very, very far away, but it's a relatively close by one. And it's one of the closest ones that has one of these super massive black holes.
Uber massive black hole.
In the center.
So how big's that one?
So this is 6.5 billion.
Holy cow.
Suns.
So we're now getting up to, I mean, I know, okay, so the Milky Way galaxy has, hundreds of billions of stars in it. But we're starting to push up towards supermassive black holes that are not too far away from the mass of the stars in entire
small galaxies.
That's nuts.
Crammed into one little black hole.
Okay, so the whole point about black holes is that everything just collapses gravitationally down to, we imagine, a singularity in the middle. It's where gravity takes over, runs out of control. There's nothing to hold it back up anymore, and it just keeps squishing down until it's maybe a point. But around that is what we call the event horizon, where that's the bit where light can't get out, right? It's so gravitationally compact. The gravitational field is so strong that anything that gets inside this particular sphere around the black hole, nothing's getting out, no light or anything. And that's kind of what we mean when we talk about the physical size of a black hole. So when we're talking about this one that's in M87, how big in extent is that black hole?
So it's they've got the really wonderful measurement now. So it's 267 astronomical units.
And remind us, an astronomical unit is
the distance between the Earth and the Sun.
Right. Okay. So how many times that?
267.
Okay. So that's quite big.
That's quite big, but it's still about the same size as our solar system.
So you've got a black hole, or at least its event horizon, the size of our solar system. So what we're talking about here is a telescope which has taken a picture. We might have to come back to that word in a minute. But anyway, take a picture of an object in another galaxy which is the size of our solar system. That's actually in itself pretty amazing.
It's very, very amazing, yeah.
Am I right in thinking that we can't typically image stars in other galaxies? I mean, very, very close by galaxies. There's fabulous pictures of Andromeda and stuff, which I always go on about, where you can see individual stars. But typically in distant galaxies, we wouldn't be talking about imaging individual things.
No. So, well, you have to put this all into a sense of scale as well. So that size of a couple of hundred astronomical units, that's not the size of the image that you're seeing. The size of the image, so the size of that bright ring that's in the image, we're looking at about 25,000 astronomical units. So there is a different
that's a
sort of
lot
scale factor that we're looking at here.
Yeah.
But that was major. The big decisions that were made to which galaxies to choose. One of the reasons was, well, we're getting down to this type of resolution with this telescope, and that's because it's so big, it's covering the whole Earth. The bigger you put, the larger distance you put between your telescopes, the higher resolution you get. And they were able to work out that with this telescope, they would be able to resolve an object on the size of a few thousand times the distance between the Earth and the Sun.
So this is possible. They figured out this one was possible. That doesn't guarantee you're going to get a decent image out of it, but it was possible. Presumably also, though, given that it is so much closer, so is the one at the center of our galaxy. So they were looking at both, weren't they?
Yes.
Were they looking at any others?
I'm not sure. I'm presuming that there will be lots of black holes out there to look at that are in the center of the galaxies. You want to go for the big ones, the ones that are kind of oriented in a good way, so that you can get to the centers of those galaxies. So I guess there's a selection process that you'd go through to find the best and the biggest supermassive black holes. It's my understanding the group of MIT that have been working on this are also working on an image of the center of our galaxy as well. But this one, because of its size, I guess really made a beautiful image, and it worked the first time. Even you put your data into the machine, churn it, and the first time it works when it comes out is just a fascinating
and there's
part of science.
So just for a little bit of clarification then, can we just talk about the size of this supermassive black hole? Like, how big is this thing? How big are we talking about?
So the size of the black hole,
the actual thing itself.
Yeah, the actual black hole. So it's we define it by, as we say, by this event horizon, which is defined by how much mass it has. So we already know it's 1,000 times bigger than the one that we have at the center of our galaxy.
1,000 times more massive.
Well, 1,000 times more massive, so more solar masses. And if you convert that to how big the event horizons are, we'll use the solar system again as a sense of scale.
Okay, because we have some sense of, we're here on Earth, the sun's over there, Pluto's out there. That's our solar system, give or take.
Yeah, so our black hole in the center of our galaxy is about 0.4 AU across.
So that's a bit under half of the distance from the sun to the Earth.
Yeah.
So, I mean, that's quite big, but it's not very.
Well, you've got to pack a million stars and suns into there.
That's a lot to fit in.
It's a lot to fit in. Which is, this is one of the reasons why we know black holes exist, because there's just nothing else that you could pack a million suns into that space to do. So the star that we talked about in the earlier episode that's orbiting this black hole that we're able to track and test general relativity.
The one at the center of our galaxy is whipping around our supermassive black hole really, really fast. Where's that?
120 astronomical units.
Okay, so that would be right out sort of towards the edge of our solar system or beyond?
Yeah, it's not too far away from where Voyager is at the edge of our solar system.
Okay, and so that's where that star is relative to the supermassive black hole. Okay, so that gives a little bit of a sense of scale. That's kind of the distance scales at the center of our galaxy. Big honking black hole and then a star whipping around it within the confines of roughly our solar system, give or take. Yeah. Okay.
So this one...
Mm-hmm. The one in M87.
Yeah, so this one is 267 astronomical units across.
Good God, that's huge. So that's a black hole the size of our solar system or more. It would contain the black hole at the center of our galaxy and that other star.
And you can't have a star orbiting too close, right? It gets kind of ripped apart by the gravity.
Yeah.
So
this is a black hole which is huge. It's the size of a solar system.
It's huge. But then you have to also put this into perspective, because if you're going to try and put now 1 billion times the sun in that space, actually that space becomes incredibly tiny again.
This just breaks your brain. This is nuts. This is silly. There's, of course, the image that's been doing the rounds and has been on the cover of all the newspapers of the black hole itself. But there's also another image which has been doing the rounds, which is fabulous, which is an image of one of the researchers, the woman who was very central to creating the image itself, of producing the algorithm that's going to go through all of this stupid amount of data and actually churn it down to, but what does that look like? And there's this great image of her. I don't know if it's a selfie or someone else took it of her, but as that first data is coming up onto her screen of her computer, looking at it going, oh my God. And it's this great image of her. You can see the look in her eyes, which is, I can't believe I'm doing this. It is awesome. What's her name?
That's Dr. Katie Bauman.
She's amazing. What a great image. And talk about someone thrust into the limelight. Who'd ever heard of Katie Bauman before this? And now she's everywhere. I think that's fabulous.
Yeah.
What a wonderful thing. So we probably should talk about this image a little bit because it's now iconic, right? It's the first time we've imaged a black hole itself, or at least its surroundings, and it gets very confusing very quickly when you start reading about. So what are we looking at? So let me throw that one to you, Emily. What are we looking at? What is this
Well,
thing?
I think we should pull this apart in lots of different ways. So we should have a look at, so what is this galaxy that we're looking at? Because it's quite different, actually, to our own galaxy, which kind of explains why the black hole is quite different to the one that we have in the centre of our galaxy. And then kind of looking at what the black hole is and what actually is a black hole. And then let's try and understand what that image is actually showing us.
Yeah, I mean, we've got an image which is, it looks like a donut, right?
Yeah.
It looks like a big orange glowing donut, and it's got a big black bit in the middle, surrounded by all of this, what looks like, brightly glowing gas. It's brighter in some places than others. It's sort of brighter around one edge than around the other side. But it's this sort of donut shape. And when you look at that and think, black hole, okay, a very basic part of your brain goes, yep, I can see a hole. That makes sense. But you think about it for a second, you think, well, what's all that stuff around the edge? And what am I actually looking at? And I thought you couldn't see a black hole. And what? So how do we start this? Where are we going to start?
So let's start with M87 because it's a lovely galaxy, and you can see some pictures taken in optical light of this galaxy. It's a very popular one to look at if you've got a small telescope.
Right.
It's really nice. So it's a giant elliptical. In fact, it's a super giant elliptical galaxy.
Sounds like everything about this galaxy is just trying a bit hard.
It's a mega galaxy.
Okay.
It's really one of the biggest ones. So
maybe that's what this should be called, is a mega black hole.
A mega black hole.
Not a super, mega. We should lead the charge for that. No? Okay.
Oh, I'm just worried we've already got a definition somewhere out there.
Oh, I'm sure there is. I'm sure there is. Okay, so M87.
So M87.
Mega
so
galaxy.
Quite a different galaxy to our own. So you've seen pictures of our galaxy, or at least artists' impressions of what our galaxy looks like. And we probably look very similar to our biggest neighbour, Andromeda Galaxy. So these big grand spirals, and you see they're kind of discs with spiral arms, and they're working in a nice sort of spiral shape where all the arms are kind of winding around each other.
By the way, if you're following along at home, links to images of all of this stuff is in the show notes. And if you're on an appropriate podcast player on your phone of choice, then you should be able to have a look at the images as well. Anyway, images are out there. Go and find them.
Yeah, so that's kind of, I think, the iconic picture that pops up into your head when you think of a galaxy.
Yeah, big spirally thing.
Yeah, but that's not what this galaxy is.
Right, so what does this one look like?
So this is kind of the other major type of galaxy that we have in the universe, which is an elliptical galaxy, which is kind of just a giant blob.
Big blob.
Big blob.
Okay, so no spiral arms.
No really interior structure to it. It's just kind of a sphere of stars that gets bigger. And sometimes it can be a bit elongated and squished into kind of a cigar-like shape. But in this case, it's nearly spherical, this galaxy, a little bit squished.
So big spherical blob of stars with massive honking black hole at the centre of it.
Yeah. Okay. And so this huge black hole, so 25,000 times the distance between us and the sun is what we're looking at. And that's the disk that's around this black hole.
Okay.
So the disk is the material that hasn't gone into the black hole yet.
Right. So this is the material which is swirling around the black hole. And we can see that. I mean, there's whole distinction between, but hang on, it's a black hole. You can't see black holes. Well, no. But you can see material which is being just whipped around this thing at incredible speeds, because when you have gas stuff swirling around an incredibly gravitationally energetic thing like a black hole, it's moving and accelerating at such incredibly high speeds that it gives off its own light. And because we're outside of the event horizon, we can see that light. It can get away. It gets bent around and distorted in unbelievable ways, but it can still get to us.
Yeah.
And so that's what we're seeing. We're seeing the stuff that hasn't yet fallen into the black hole.
exactly. And this black hole is feeding. It's not a huge feeder, if you like. There are other black holes that are consuming more per day or per year.
So when you say feeding and consuming, what you're saying is some of this stuff is actually spiraling down and falling into the black hole. And so the black hole is getting more massive.
Yep.
So how do we know that?
So that's the energy outputs that's coming in. So part of that feeding process, and for this black hole, it's about the mass of the sun every 10 years.
Right.
Which is pretty modest for a black hole of this size.
When you consider that it's, how many billion solar masses?
Yeah,
so it's going up by a small fraction of a percent every 10 years. Yeah, okay, so it's not voracious.
But what that does is there's a lot of physics that happens when you accelerate matter to these ridiculous speeds. And so you've got your disk that's going around your black hole, and then perpendicular to that, you end up with some of that energy being pumped out in the form of a jet.
Right, okay, so I'm imagining now, black hole at the center, disk of stuff, gas, dust, stuff, swirling around, giving off energy, but then as you're getting all of that energy swirling down around the black hole, some of it's getting funneled out sort of along the poles of this thing. If that disk is around the equator, then around the poles, it's spitting out these incredibly energetic jets. And we can see those, I assume.
Yeah, M87 has a beautiful big, it seems to only have one jet that's pointing kind of not towards us, but in a direction that we can see it coming out of this galaxy. So that you can see in radio. It's also got huge amounts of high energy radiation coming out of it as well. I think what we have to remember with these black holes is that they are some of the most extreme environments we have, right? So our kind of physics of our everyday living room, things that are going on in here.
That's not happening anymore.
The electric fields, the magnetic fields, the gravity, all these things are just like on steroids, right? And so it does make a lot of weird and wonderful physics happen. And this is, so when we unpack the image of what we're looking at, we have to remember that this is weird. Like, this is not your everyday kind of planet going around the sun even scale of gravity.
Yeah, normal rules do not apply here.
Yeah, so we have to really be careful how we interpret that. Because it's very easy to just say, oh, you've got, as you say, you've got this whole sort of darkness in the center of a bright bit. Well, maybe that's just a black hole with some glowing stuff going around it.
Yeah, it's not that simple,
it's
though, is it?
It's not that simple.
No, especially when you start thinking about this thing in 3D. Okay.
Yeah.
So let's start unpacking that a little bit. So it does look like, when you look at this image, it does look like a black hole in the middle of a bright orange donut. And that kind of implies, well, we're looking at this sort of, head on. We're looking right down on top of it, and the ring's going around the outside and the black hole's in the middle. And as it turns out, that's kind of a little bit true, but that's a bit misleading. That you said that the jet that's coming out of the black hole or out of the system is pointing kind of mostly towards us. And so we are, in a sense, looking down on this thing. But that's not why we're seeing the ring. That's coming from different weird gravity physics, isn't it?
Yeah, and this is, I mean, if you've ever wanted to think about things like invisibility cloaks and things like this, what you need to do is to bend light. And maybe a good way to think about this is to think about something that's more kind of intuitive and more everyday, which might be something like, let's say, a planet going around a star. So the way gravity works, gravity doesn't care whether you're talking about a planet or you're talking about light, right? It bends those objects under exactly the same laws of physics, right? So if we're going to be talking about photons orbiting a black hole.
Which is weird, because you normally think about light going in straight lines, but that's kind of the whole point of general relativity. Einstein's big theory from 100 years ago is, when you talk about straight lines, you're not talking about straight lines through flat space anymore. That heavy things, massive things, bend space-time itself. And so around a black hole, it can be bent so much that the light travels in a straight line, as far as it's concerned, around and around and around and around and around this incredibly, stupidly massive black hole, which is amazing.
Yeah, so, well, let's imagine that you had a rocket and you were going to send it towards the sun, right? If you sent it directly towards the center of the sun, it would, and you gave it enough speed, it would just go straight into the sun. You'd lose your rocket, and it would probably be a pointless exercise.
Be fun, but waste of money.
Yeah. Yep. But if you sent that rocket at an angle towards the sun, then there's a few different things that can happen. If you send it at a very sharp angle, so quite close to the edge of the sun, then that rocket's going to bend around the sun because the sun's gravity is going to pull it into kind of an orbit, but it might have a bit too much pull, and so it kind of spirals down and then eventually gets incinerated in the sun. If you put your rocket at just exactly the right angle and with exactly the right speed, then you're able to get your rocket into orbit. And then it will be like another planet, right? Going around the sun. It will merrily just go around and around and around and won't spiral in or won't spiral out. And if you give it a bit more than, if you go to an angle a bit more than that, then you can get a little bit of bending, but then the rocket will still fire off back out into space.
Right, so it'll go head off into space, but at a slightly different angle from the way it went in. So there's three possibilities, and like you can see that with a rocket. That's fine. The really cool thing is that, well, light's just another rocket, really, as far as this stuff's concerned. It can do the same thing. It can spiral into the black hole. It can orbit around and around and around and around forever. Or it can be bent and escape, but in a completely different direction.
Yeah. So if you were sitting on the Earth and you imagined sending your rocket and it went at the right angle, went all the way around the sun and came back round to Earth, if you did that with a photon, with light, what you'd be able to see is you'd be able to see the Earth, but after it's gone around the sun, because that photon's carrying the image of the Earth.
Right. Yes. Okay. I can see that. So relating that kind of idea back to this picture then, stuff like light that's coming at the right kind of angle from behind the black hole, which we wouldn't normally expect to see, it's perfectly possible for that light to be bent really quite severely around this black hole and come down to our eyes and our telescopes, because we're talking about radio waves, so we wouldn't see it anyway, but down to our telescopes, from an angle that is utterly different from the angle that it left originally. What that means is that the stuff that we're seeing, that bright donutty bit, is light that's coming from gas spiraling around this black hole, some of which is actually behind the black hole. Like it's been bent around so that we can see over the top and down behind this thing, which is cool.
It's very cool.
It's almost like the black hole's acting, well, it's very much like the black hole's acting like a lens. It's acting like a gravity-based gravitational lens. It's picking up the light behind it and bending it around and dumping it down towards us in really interesting ways.
Yeah. And that photon, or that photon's path, it's picking up the light from all the different gas clouds that are on all the different parts of that photon's path as it goes through. Well, you get more and more photons from each different gas cloud. But if you imagine this trajectory, you're just adding more and more photons from every single gas cloud, and you're picking them up from all different angles. So it's you get that kind of addition effect. So the photon carries lots of different bits of light with it. Well, lots of photons.
Yeah, I mean, it's very cool. We're seeing the equivalent of, in popular culture, and I think we talked about this in episode 20, the film Interstellar, which was famous in at least physics circles and astrophysics circles for trying to portray a black hole in the most physically accurate way possible. And they got pretty well-known physicists and astrophysicists involved in the design of that thing. And so there's the iconic images from that movie of this crazy shaped thing where it kind of looks like, you've got a black hole with all of this ring of light around it, but the ring's been distorted and bent around it in weird ways. That's what we're seeing. And one of the really big things to come out of this photo is that it's actually confirming, yeah, that's right. That's exactly what happens. You really can see the stuff behind it because of this gravitational lensing thing. So that's very cool. One thing that we haven't talked about yet is, so the donut seems to be glazed more brightly on one side than the other. It's not uniform brightness around a black bit in the middle. It's brighter on one side than the other. Why is that?
So this is a great example of, again, this is extreme environment physics, right? So in our everyday life with gravity on the Earth, then we can just use approximation of Newtonian gravity. An apple falls out of a tree, it hits the Earth, it's fine.
Yep.
You don't have to make any very difficult corrections to your maths to be able to calculate
Newton got
that.
it right to a very good degree of accuracy, but not in this kind of environment. This is different.
Yeah, and so then you have special relativity, which looks at the fact that light has a finite speed. Therefore, you get some interesting effects when you travel very quickly right, when you're traveling close to the speed of light. And then Einstein developed that further into general relativity, which explains how space and time change the way that photons and mass interact. And so this is you can't go looking at the maths of a black hole without invoking general relativity.
Well, you don't get black holes without general relativity. I mean, it's entirely entwined in this theory. Without it, you've just got a vague idea. But in general relativity, it actually comes out of the equations. You know, it wasn't Einstein himself, but I don't remember who it was. Do you remember who the astrophysicists were who first calculated that? I can't remember their names. We'll have to look it up and put it in the show notes. But it was a number of years after Einstein came out with this theory that someone went, so if you had a really big star and it ran out of fuel, you'd get one of these things. Don't know what to call it, maybe black hole, but it's really weird. We should look into that some more. And it comes straight out of the equations. It's amazing stuff. But it also means that all the weirdness that comes with general relativity is inherently built into the whole concept of a black hole.
Yeah. And so this bright bit that we're seeing, it kind of looks a little bit like a smile, I think, is a relativistic effect, and it's called Doppler beaming. And what's happening here is that the photons that are coming towards us appear to be a bit brighter. So you get part of this, you're imagining a sphere. It's called the photon sphere, actually, that's around the black hole. So this is where the photons are able to escape, but so they're able to come towards us. Because if they couldn't escape, we can't see light.
We wouldn't see
coming
anything.
Right?
That's the point.
So it's just outside of this event horizon. And so these photons are kind of going in, they're spiraling around maybe many, many times, and then able to kick out again. And the ones that are coming directly towards us get this boosting effect from the fact that they're traveling, and the Doppler effect means that they get pushed to being brighter as they're coming towards us.
Right, as they're being dragged around in this incredibly intense gravitational field and being bent around this black hole, that relativistic Doppler effect is making them look brighter. And so conversely, going around the other side, when they're being bent around away from us, they're looking dimmer. And that's what we're directly seeing in this image.
Yeah, and it's almost exactly half the circle, right? That's the brighter half. So that's the half of it that's coming towards us.
So that's exactly what you'd expect to see.
Yeah.
Well done, Einstein, and all involved.
Yeah, it's great. It's fantastic. And you can see a little bit of the blobbiness, which comes from the fact that there's different kind of chunks of gas. So there's very slight instabilities, or different changes in brightness across the ring. You're seeing that the ring is brightest, closest to the edge of the rim, if you like, where you can't get photons from, because that's where the gas is hottest and it's emitting the most light. So yeah, there's lots of wonderful, wonderful physics that just fall out of this image.
Which is amazing when you consider that it's not a particularly high resolution image, but it has made me smile wryly in a sort of actually really annoyed kind of way, that there's been all of these hot takes on the internet of people saying, well, it's not a very good image. It's like, hang on, just back up a second. And I think one of the best responses to that I saw, I can't remember who it was, I should look it up, was someone saying, to everyone who's saying, oh, it's a bit of a fuzzy image, feel free to send me your pictures of a black hole anytime. And I think that's a fair point. This is an incredibly difficult thing to do. But the flip side to that is it is amazing how much you can get out of a pretty fuzzy image of a bright donut in a galaxy a very long way away. You can really extract a lot of, yep, that's general relativity right there. That's what we expected to see. And look, it's there. That's awesome.
And we've had models which have been so good at predicting exactly what we're seeing. So when the image was processed, you're able to generate what kind of models would fit, like what the characteristics of the black hole that would fit the image that we're seeing. And so this is not a simple black hole. So Hawking's black hole that he sort of started to describe mathematically, which uses the Schwarzschild radius. This is the event horizon beyond which photons can't return. His original calculations didn't include the fact that the black hole rotates.
Yeah, I mean, just doing black holes at all is challenging.
Oh, yes.
This is not simple mathematics. And Hawking came along
do not want to downplay what the amazing
nice work.
Stuff, yeah.
But it was the simplest possible case, which is imagine nothing's rotating at all, which never happens, as far as I can tell.
Everything we find in the universe rotates, right?
But, in that great physics way, which is, let's just get rid of all possible complications. If it wasn't rotating, what would it do? And you get a black hole with particular properties. But, of course, if it is rotating, that makes the maths a bit harder. But a bit later on, other people came along and started to figure that one out.
Yeah.
And so presumably this one's rotating.
It is. And so that's the Kerr solution to black holes. So Kerr looked at, okay, well, this is a black hole. What happens if we give it some angular momentum, which means what happens if it rotates?
Yeah, and Kerr, we like Kerr because he's a Kiwi.
Yeah, definitely. And I had a lecture from him, actually, when I was an undergraduate. So
Very exciting.
Kind of like, famous people. Very cool. And so, I mean, you say the maths was a bit harder. Oh, my word. I've seen some of that maths, and my goodness. It changes a lot of the really interesting properties of the black hole. You end up with more than one event horizon. You end up with photons which can appear in places you wouldn't expect them to. But it's so exciting.
As if it wasn't hard enough.
I know. It's just, it makes the whole situation just amazingly complicated.
I didn't do a lot of general relativity in my degree. I left that behind pretty much as quickly as I could. But it really does break your brain. It's worth it, if you're out there thinking about doing it. Have a shot. Go and read up on it. But wow.
It's fantastic. Yeah. And what happens is you can end up making predictions of what you're going to see under different scenarios. And in this case, you could look at rotation of the black hole, and you could look at rotation of the disk. So those are two kind of linked but distinct objects, right? So you could say, is the black hole rotating in the same direction as the disk, or is it rotating in the opposite direction to the disk?
And wouldn't you kind of expect that they're the same? Like, okay, take our solar system, right? Are we orbiting the sun in the same direction that the sun is spinning?
We are.
And that makes sense to me because we've all come from the same thing.
Yeah, we all came from the same rotating gas cloud, so we kind of all share the same rotation.
So wouldn't that be the case here?
Well, no.
Oh, because black holes.
Because black holes.
Right. We're not going to take your rules. We're going to do our own thing.
It's amazing. So we're able to say that this black hole is spinning in the opposite direction to the disk that surrounds it.
Nuts.
Amazing.
Nuts. And they can tell that from this image.
Yeah. You can have a look at the paper. You see this lovely chart of this is what the image would look like if it was spinning in the same direction. This is what the image would look like if it's spinning in the opposite direction. And it's completely... it's obvious that it's the one that's spinning when they're opposite.
Nuts. Explaining that is another matter. I mean, how did that happen? But here we are. I mean, I guess you could imagine, given that this thing is so massive, it's been around for a very long time. Its original rotation could, whatever original gas cloud that had the rotation that ultimately formed the original black hole, is long gone. And what we're looking at now is something else that's been captured, which was going in a different direction. Something that massive is not going to be affected terribly much by whatever comes along next.
Yeah, and this is starting to point us in some really interesting ideas about where did this black hole come from then? Because it's so much bigger than the other black holes, like the one we have at the center of our galaxy.
Yeah, what did we say, 1,000 times bigger?
Yeah, how do you make a black hole that big? So one idea is that perhaps actually the black hole predates the existence of the galaxy.
Oh, wow. So maybe it's sort of, I don't know, did it form a nucleus for the galaxy or?
Yeah, so traditionally we think that galaxies formed and then they had the black hole at the center that they formed with that. But in this case, maybe it's the other way round. So maybe the black hole came first and the galaxy kind of formed around it.
Wow, that's cool.
Yeah. Or, the other ideas, maybe we had mergers of galaxies. Elliptical galaxies are often thought to be mergers of big spiral galaxies like our own.
Okay, so when you got a couple of galaxies which do have a lot of structure in them merging, you'd get an enormous amount of disruption in that structure and ultimately just end up with a big blob.
Yeah, and if the two supermassive black holes at the centers of those two galaxies came together, then you could get weird, effects and get things spinning in different directions.
Yeah, so that would kind of help to understand why you'd have this huge black hole spinning one way and the disk of stuff around it going the other ways. Because, hey, black hole's been around a lot longer than you have, pal. Nothing you can do about that because I'm huge.
Yeah, so that's one of it seems like you can take this simple image and it's just like, well, did you just make that to become famous on, the media? But no, this is science. Images in science can tell you a lot of information about the physics of what's going on. I mean, as we've, black holes are some of the weirdest objects in the universe. We want to understand what happens to matter if you make it super, super hot, if you put it in insane gravitational fields, if you put it in incredible magnetic fields, what happens? If you put it in, the crazy places in the universe that we can test the utter limits of what we know with the physics we have. And
a little bit like the there was the observation not long ago of the gravitational waves from the black hole mergers and then the neutron star mergers, right, with LIGO. The first one of those was, oh my God, we can see this at all. And then it starts to become a bit more like, no, this is a whole new branch of thing. Now we're getting more and more data and we're able to get statistics and start to figure out how do we use this information to understand much more than we could from just the original direct observation of it exists. And presumably this is going to be similar. That this is not the first. Oh, sorry, this is the first one of these, but it's not going to be the last.
Oh, no, by no means.
No. Once we've shown we can do it, then, okay, let's find more. Let's go and look at them.
Yeah. So in some ways, this image reminds me a little bit of the pale blue dot image.
Yeah, another iconic image. So that was from Voyager when it was out near... Is that the one where you're talking, looking back through...
Yeah, looking back from beyond Saturn.
Yeah. And there's this iconic image of looking back towards the Earth, and the Earth is literally one pale blue pixel in that image, or one pale blue dot, smallest part of that image you can be. And that's us. That's all of us. And it was... When was that? The 70s?
Yeah.
And it became this iconic image of, everything that's ever happened on Earth in our species and beyond is that dot, that pixel. And it's iconic for that reason. This image is iconic for similar kinds of reasons. This is the first way that we've been able to see something of this extraordinary magnitude, and also something which we figured out from the equations ought to be out there, and now we've seen it. Like that's a big moment.
It's huge. And so coming back to Katie's picture, I think I love the photograph. She's got her hands over her mouth. She's just got this look of kind of terrified, almost joy in her eyes.
It's like looking at a kid opening their most treasured present on their birthday. It's just that look of, oh my God, I'm 5 years old and this is so exciting. And that's a grown-up scientist. It's so inspiring.
Science is not always dry and writing out equations. Science is, it makes your heart leap at times, when you get these exciting things. It's 100 years this year since Einstein's first relativity was tested by looking at the solar eclipse and seeing the bending of light from background stars that the sun does. So it's in some ways a really nice kind of circular thing that we're now testing the extreme theories of Einstein's predictions around black holes. And that reason I came across, my colleague actually pointed me in the direction of this quote from Einstein, which, if I may, I think kind of applies maybe a bit to Katie as well. He wrote to one of his colleagues after he was trying to describe the variations that we saw in Mercury's orbit using his relativity equations.
Yeah, which can only be described by his equations. If you apply Newtonian stuff to Mercury, you get most of the answer, but there's this little bit left over that says, no, it shouldn't do that. That's wrong. And only Einstein's equations could explain what was going on because it's so close to the sun. Yeah,
so he was pumping through the maths and he came to answer the answer, and the answer perfectly matched the discrepancy in the observations. And he wrote to a colleague, and the quote is, "For several days, beside myself with joyous excitement." And I think when you look at Katie's picture as well, that quote just perfectly matches that as well. The joyous excitement of science and what you're doing. And to me, that really brings home the wonderful relationship that we have and the human nature of science as well.
Well, Well, that brings us to the end of this black hole-tastic episode of Syzygy. This one's been a long time coming. I've been waiting for this one since episode 20. And then actually, it turns out when the news dropped, Emily was away. I'm not blaming you, Emily. But
I was up
you
a
were
mountain.
away. You were up a mountain, and I had other stuff going on, and we couldn't do it at the time. But we've done it now, and I'm really glad we have, because I just, I love this stuff. Sure.
Got me a chance to get my general relativity textbook out and
Exactly.
brush up on that stuff.
Every once in a while on this show, you kind of got to, hang on, Google's not going to do it. We've actually got to turn to real books on this one. Go and talk to people. It's great stuff. But we do have to wrap this one up here. So, look, if you're interested in going back and listening to episode 20, or indeed any of the other episodes of Syzygy, there's a way you can do that. You can go and check us out at syzygy.fm, and you will find all of the past episodes, all the show notes, all the images that we've found, plus, a whole bunch of really cool astronomy, astrophysics, and cosmology in there as well. But that's not the only place you can find us on the interwebs. Emily, where else can people find us?
Well, if you happen to be a light year away from Earth, then you're going to be able to get Syzygy soon.
That's true, actually. Yeah, we really should. I think we talked about this before. We should have cake.
Yeah.
We should have light year cake.
Yeah.
I like that.
So if you're just coming up to a light year away, then Syzygy episode 1 is heading towards you.
That's right. Beamed out into... Although, we're not beaming, really, are we? I mean, a podcast is all kind of over the interwebs. But someone, surely somewhere, has got an antenna.
I'm going to start beaming it now.
Okay,
then.
all right. In that case, we should have cake in another year's time. Whatever. Point is, we're almost a year old, give or take.
If you're quite closer than that, then you can hook us up on Twitter.
That works too. Yeah.
So we're at SyzygyPod.
I don't think Voyager has Twitter, does it?
It's probably got its own Twitter, surely.
Yeah. Anyway, yes, at SyzygyPod. And in fact, at SyzygyPod anywhere. If you're wondering whether we're on a social media platform, just check out at SyzygyPod, and that'll be us. We're out there on the Instagrams, on the Facebooks, and on the Twitterverse and all of that. And you can go and find us and see what we're up to this week. You'll see when new episodes drop. You'll see when we find stuff that just tickles our fancy in that particular week.
Yep, I read a really good article today.
Did you?
I'm going to tell you all about it.
Is this going to be a future episode?
It may well be.
Excellent.
Stay tuned.
Good. One last thing. If you want to help to support the show, then you can do that in a number of ways. You can spread the word. Tell your friends, tell your family. There's this great show where they talk about stupidly big black holes, and it's great because that helps other people to find us. The other way people can find us are through you leaving reviews on your podcatcher of choice, on Apple's podcasts, on Google Podcasts, on Spotify, wherever you find us. Send us a review. Give us some stars, and that helps us to rise up through the noise, and it helps us to share the joy of this stuff with the world. But we'll be back to share more of this stuff with the world in probably a couple of weeks' time. I think over Easter, there's going to be a bit of a break. I'm certainly heading away. So, yeah, we'll be back with some more stuff, whatever Emily's got up her sleeve, in a few weeks' time. Until then, thanks for joining us. Talk to you soon.
Catch you later.
Bye.